Today we're going to use our knowledge on perpendicular bisectors to talk about 5-2, which is the circumcenter of a triangle. So first we're going to look at the perpendicular bisectors of a triangle. So I drew a triangle here, triangle ABC. Now we know what perpendicular bisectors are. We just talked about them in 5-1. Just looking at the word, perpendicular means it forms a right angle, and bisector would mean it cuts a segment in half. Well, if we look at a triangle, we have 1, 2, 3 segments. So there must be 3 perpendicular bisectors. So I'm going to go ahead and draw these 3 perpendicular bisectors. I'm going to do my best, being that I'm freehanding, I'm going to do my best to look at them. But here we are. We have one, and this is nearly in the middle. It's going to be perpendicular. It's nearly perpendicular, and it looks like it bisects. And then we have, let's look at AB. That one is not bad either. And then lastly, we'll look at BC. We look right in the halfway, which is about here, and we need to go perpendicular. So we're going halfway, and then we go on perpendicular, and we get here. And again, my drawing is slightly off, but you can do this over and over again. It's actually a pretty good construction with paper. But what we see is that all 3 points came to one, or all 3 lines came to 1 point. We call this a special word. And we call this word concurrent. Concurrent is when at least 3 lines intersect at 1 point. So we would say that these lines are concurrent because they meet at 1 point. In fact, that point that we call it is the point of concurrency. And it's simply the point where at least 3 lines intersect. And only in a triangle, in this specific case, we dealt with the circumcenter of the triangle. But this happens only in a triangle. You have the circumcenter of the triangle, and it is the point of concurrency of the 3 perpendicular bisectors in a triangle, as we have here. That's a very special type of point of concurrency, which is the circumcenter. We have a theorem that deals with the circumcenter of a triangle, so that's let's go talk about that now. Theorem 5-2-1, which is called the Circumcenter Theorem, says that the circumcenter of a triangle is equidistant from the vertices of the triangle. So let's go ahead and look in a diagram what that looks like. Now we have a triangle A, B, C, and we need the circumcenter. Remember, the circumcenter deals with the perpendicular bisectors. So drawing in our perpendicular bisectors, again, I apologize if I'm off slightly. That looks like through AC, perpendicular bisector through AB would be about right here, and through BC is going to be about right here. Now we have our circumcenter, which is this point where they all intersect. Now what our theorem says is that the distance from the circumcenter to all of the vertices will be congruent. So I can go from our point, our circumcenter, and we can go to point C. And then we can go to point A, and we can go to point B as well, which appears to be right there. Now what our theorem tells us is that these distances are all congruent, and that's kind of cool, but also it's kind of obvious. If we think back to 5-1-1, if we think back about the perpendicular bisector theorem, what does it tell us? It tells us that the perpendicular bisector tells us that any point on the perpendicular bisector is equidistant to the endpoints. And that's why I said that it's kind of obvious about this circumcenter theorem, because we do have a point on the perpendicular bisector. So we have a point on the perpendicular bisector, and so obviously it's going to be the same distance. But then we just keep talking about, then we're on this perpendicular bisector, so we have congruent again. And it just continues. So that's where that theorem comes from, and that's where the proof would come from as well. One important thing that you must know is that circumcenters are not always inside a triangle. That may seem confusing. Now, everything we've looked at is an acute triangle. Think about an obtuse triangle. If we were to draw an obtuse triangle here, and we can draw on the circumcenter real quickly. We need the perpendicular bisectors again, about there, and let's go about here, and then the other would be about right there. Now, as you see, this is outside the triangle. A obtuse triangle will give you a circumcenter outside. And again, that was for an obtuse triangle. The last type of triangle that we have not looked at is a right triangle. So let's go ahead and look at that. We have our right triangle, so now we need the perpendicular bisectors. We have one about right here. We have another right here. And then lastly, our other is about right there. Now again, I did not draw it exactly perfect because this is freehand, but we notice that we have a circumcenter on the triangle. And this will happen when you have your right triangles. So these are important things to know again, is that a circumcenter is not always inside the triangle. But your circumcenter theorem still holds true, meaning that our point out here is still equidistant from all the vertices. Same with the right triangle. It is still equidistant. So your circumcenter theorem still holds true. They just don't have to be inside the triangle. Okay, our directions here tell us that, and we do have an example. We're going to see how we can use the circumcenter theorem. We have segment KZ, LZ, and MZ are all perpendicular bisectors of this triangle, triangle GHJ. So we have two things we want to do. The first is to find the length of GM. I noticed it was length because there's no bar over GM, so we want to know the length. Second is to find the length of JZ. Also, if you'll notice in blue, we have our diagram. In blue, we have some lengths all scattered throughout here. Segment KZ, it's important to note we're talking about KZ. These are the perpendicular bisectors in here. Because it's kind of scattered, we got a lot of segments going on. So to find GM, let's start with number 1. Besides looking at a car dealership, where's GM? GM, we're looking for this length right here. Well, what can we do? Let's think here. Well, we know that MZ, right here, is the perpendicular bisector. What does that mean? Because it's a perpendicular bisector, 1, we know we have a right angle. Doesn't help us very much, but we also know the word bisect. Bisect means we are cutting in half, right there. Because these two segments are cut in half, we instantly know that we have two congruent segments, as you see here. So therefore, we could say that GM, the length of GM, is equal to the length of MJ. What that means then is that GM is equal to 14.5, and we would be done right there. So number one, we are done, and we didn't even use the circumcenter theorem. All we used is the idea of perpendicular bisector. Number two, let's see if it's a little bit different. For number two, we're trying to find JZ, short of with Beyonce. So JZ, J to this middle there. This is a slightly different problem here. What we could do, though, is that we know, well, JZ. It looks like we have LZ, KZ, and MZ. These are all perpendicular bisectors, meaning Z, that middle point, is the circumcenter. Because it's the circumcenter, we use the circumcenter theorem. Let's use, I'll go ahead and write that down. Because we are dealing with perpendicular bisectors, we should use the circumcenter theorem. More in depth, more of a reason is because they all intersect at the same point. You can't just use it if we're talking about perpendicular bisectors, but because all these perpendicular bisectors intersect at the same point, we should use the circumcenter theorem. So the circumcenter theorem, what that tells us is that this point Z is the same distance to all of the vertices. Well, do we know the length to any vertex? Well, yes, we do. We know it's 19.9. And so therefore, we could say that GZ is equal to HZ is equal to JZ. We know that GZ is equal to 19.9, and so then we can say that JZ is also equal to 19.9, and that one was using the circumcenter theorem. So we're done now. We did the two problems using different ideas. We used the idea of perpendicular bisector and the idea of the circumcenter theorem. We're going to wrap up here, but not before we summarize. The first topic we talked about is that we can use a circumcenter theorem when we have at least three, I didn't say three, sorry, when you have at least three perpendicular bisectors of a triangle intersecting. That's when you should be thinking about the circumcenter theorem. The second point is that a circumcenter can occur outside of a triangle, and that happened when we looked at a right triangle or an obtuse triangle. And lastly, and most importantly, the circumcenter theorem says that the point of intersection will be equidistant to the triangle vertices. I did capitalize vertices because we'll notice that that is not true for future things we talk about. For the vertices of a triangle, the distance will be equal. Anyway, that is what we talked about with the circumcenter theorem. Hope you guys understand, and that's all I've got, so go ahead and have a great night, guys.